Alright, so periodic table, chapter 4, periodic table. From the last chapter, we learned a few little things about periodic table. We know that in periodic table, we can classify all the element here. All the element here, we classify them as block element. All the element in transition metal, we classify them as the D block element. And all the element in group 13 anti-noble gas, group 18, we classify them as P block element. How do we classify them as block element, D and P block element? Based on their valence electron. Based on their electronic configuration. From the electronic configuration, we know their valence electron. So then we can classify them based on their valence electron. So all the element in S block element, all the element in S block element, the valence electron are in the S orbital. All the element in P block, the valence electron are in the P orbital. Also in periodic table, we have the two terms. One is group and second term is the period. So group is for all element going down. Here we call them as the group. We call them as a group 1, group 2, group 13, group 18. This is group. And period is all the element in the horizontal row. All the element in horizontal row, we classify them as in one period. We have period 1, period 2, period 3, period 4 until period 7. So these are the two terms that you should know, period and group. What are the differences? So group, all the element in the same group, all the element in the group 1 and all the element in group 2, they have the similar valence electron. So all the element in group 1, the valence electron is 1. All the element in group 2, the valence electron is 2 electron. And the list goes. So in group 13, the valence electron is 3. And in group 14, the valence electron is 4. And group 15, valence electron is 5, and so on. Okay. Now is period. So period, we classify all the elements in the same period as they have the same principal quantum number n, as they have the same energy level. So all the element in period, as example, all the element in period 2, lithium, beryllium, boron, carbon, and so on, they have the same energy level. They have the same principal quantum number. The value of n is same. So value of n for period 2 is 2. So in the energy level, the highest energy level that this element can achieve is energy level 2. The highest principal quantum number n that this element can achieve is principal quantum number n2, because they are in the period 2. If they are in the period 4, so this element, all of these elements in period 4, the energy level, principal quantum number n is 4. And now we go to the trend in periodic table. We have 4 trends that we're going to discuss. One is atomic size, also ionic size, atomic and ionic size, electropositivity, electronegativity, ionization energy, and electron affinity. So we discuss each of them. So atomic and ionic radius. What is the atomic radius? Atomic radius is the distance between two nucleus of the same atom. In diatomic molecule, as example, we have helium atom here. This is helium atom. This is another helium atom. So we call this as the diatomic atom. So the distance between these two nucleus is, we call them as the atomic radius. So what is the trend of atomic radius in the periodic table? So at the atomic radius across the period, we have periodic table. So across period, the atomic radius is decreased. Why it decreased? Because the ZF value is increased. What is the ZF value? ZF value is the nuclear charge energy. Nuclear charge. ZF is the nuclear charge. So across period, atomic radius decrease because the ZF is increased. So that what will happen to the trend in atomic radius in period. For the atomic radius trend going down the group, so the atomic radius increase. As we going down the group, the atomic radius increase because the shielding effect increase. So what are the nuclear charge, what are the ZF, and what are the shielding effect? Effective nuclear charge ZF is the total amount of attraction of a nucleon towards, the total amount of attraction of an electron towards the nucleus. So tarikan elektron kepada nucleus. So that is we call as effective nuclear charge ZF. So the value of ZF depends on the value of the electron. So how to calculate ZF? Approximately by the value of by this equation, which is the value of proton minus value of electron in the inner orbital. Value of proton minus value of electron in the inner orbital. So then we can get the value of ZF. So that is the F. Across period, atomic radius decrease because increase in ZF value. As example, we see here lithium, beryllium, and boron. These all are in period 2. If I'm not mistaken, these are in the period 2. Yes, these are all elements in period 2. So across the period, as you can see, the atomic radius is decreased. This is higher, this is larger atomic radius, this is smaller atomic radius. So across period, atomic radius is decreased, ZF value is increased. So the ZF value for lithium is 1. How you get 1? So number of proton minus the electron in the inner orbital. So how many number of proton in lithium? 2. In lithium, number of proton is 3. 3 minus how many electron in the inner orbital? We have, this is inner orbital. 1s2 is the inner orbital, 2s1 is the outer orbital. So how many electron in the inner orbital is 2. 3 minus 2, you get 1. So ZF value for lithium is 1. ZF value for beryllium is 2. How do you get 2? So beryllium proton number is 4 minus 2 electron in the inner orbital, and then you get 2 for ZF value. In boron, the proton number is 5. Proton number is 5 minus 2 electron in the inner orbital, so the ZF value is 3. So across period, atomic radius is decreased because of the ZF value is increased. ZF value is the attraction between the nucleus and the valence electron. Second terms, besides ZF value, is the shielding effect. Shielding effect describes the attraction between shielding effect describe the repulsion between the inner electron to the outer electron, between the inner electron to the valence electron. So the repulsion between this electron, how many, what are the value of the repulsion, higher or lower? So the higher the repulsion, the higher the number of repulsion, the bigger size of the atomic radius. So across period, atomic radius decrease because of the ZF is increased. Going down the group, the atomic radius is increased because the shielding effect is increased. So what are the shielding effects? What are the ZF? What are the ZF nuclear charge? The shielding effects, and what the definition of the shielding effect? What are the definition of nuclear charge? So these two you have to know. Okay, now we go to the trend of ionic radius. Ion, we have two types of ion. One is cation and another is anion. So cation is when we remove electron from the valence orbital, so it will form cation. Size of the cation, the radius of the size of the cation are smaller than their parent atom. As example, we have beryllium atom and we have beryllium ion, beryllium 2 plus, for example. So the size of beryllium 2 plus is smaller than the size of beryllium atom. Why it becomes smaller? Because the cation, the valence electron, because the valence electron in the cation experience larger ZF, experience larger nuclear charge than the valence electron in atom. So then it will shrink the ion more than the atom. Maksudnya, in beryllium we have 4 electron. In beryllium we have 4 electron, 1s2, 2s2. So this is in beryllium atom. In beryllium ion, electron is 1s2. 2 electron from the valence orbital is removed, and when we remove this valence electron, the attraction of electron in 1s orbital towards the nucleus is higher. The attraction of nucleon towards the nucleus is higher, and when the attraction of electron towards the nucleus is higher, so the ZF, the effective nuclear charge, will also be increased. So and then it will make the ion shrinking in size. Compared to beryllium, we have 4 electrons here in beryllium. So the nuclear charge, effective nuclear charge in beryllium atom is lower than the effective nuclear charge in beryllium ion, in beryllium 2 plus ion. So then the size is much bigger than its beryllium 2 plus ion. So this is what happened in cation. When we remove electron, so the effective nuclear charge will be more bigger, it will be more higher, and then the size will be more smaller. In anion, to form an anion, we remove electron. To form an anion, we accept electron. We attract electron. So when we attract, we accept new electron, adding into the valence orbital. So the repulsion, the shielding effect, the repulsion between the electron in the valence electron, the repulsion between electrons in the valence orbital to the electron in the inner orbital will be bigger, meaning that the shielding effect is higher. So then the anion have a larger size rather than their parent atom. So fluorine atom, size of fluorine atom is lower than size of fluorine anion. Size of fluorine atom is lower than size of fluorine anion. Size of fluorine anion is much bigger than the size of fluorine atom. Why? Because in fluorine anion, we add a new electron, and when we adding this new electron, the repulsion become higher. When the repulsion become higher, the shielding effect will become also increase, and then the size of the atom will be larger. Okay, next, this on this slide, you boleh baca sendiri. Okay, next we go to isoelectronic. So this is important. What are isoelectronic? Isoelectronic is chemical species that have same number of electron. Species that have same number of electron. So it can be ion, it can be atom. For example, sodium ion is an isoelectronic to neon atom. Why? Because the electronic configuration for sodium plus ion is similar to the electronic configuration of neon. Neon is 18 electron. Neon is 10 electron. Neon is 10 electron. So electronic configuration for neon is 1s2, 2s2, 2p, 1s2, 2s2, 2p6. So this is 1s2, 1s2, 2s2, 2p6. So this is electronic configuration for neon. For sodium ion, sodium is 11 electron. Sodium is 11 electron. To become sodium plus, we have to remove 1 electron. So when we remove 1 electron, the original electronic configuration for sodium ion is 1s2, 2s2, 2p6, 3s1. So when we remove 1 electron, we remove electron from the 3s orbital. So the electronic configuration for sodium plus ion is similar to the electronic configuration of neon atom. So that's why we call them isoelectronic, because these two species of chemical having the same number of electron and the same electronic configuration. Okay, next is the isoelectronic, the trend of isoelectronic in cation and anion. So when going down the group, the principal quantum number and the energy level increase, causing the cation to get larger. So when we going down the group, the size of cation increase. When we going down the group, size of cation increase because the energy level, because of the principal quantum number, increase. So across period, it will increase the nuclear charge. It will increase the effective nuclear charge for isoelectronic cation, causing the cation to get smaller. Across period, um, the isoelectronic cations, meaning that this cation have the same number of electron. This cation have the similar electronic configuration. So across period, for this isoelectronic cation, it will the size will get smaller. The size of the isoelectronic cation will get smaller because of the nuclear charge is increased. Sodium, magnesium, aluminium, all these elements are in the same period. Sodium, magnesium, element, all these elements are in the period 3. And sodium plus have the same electronic configuration to the magnesium 2 plus, have the same electronic configuration to the aluminium 3 plus. So these are isoelectronic cation. So across period, the isoelectronic cation will become smaller. Sodium plus size of the sodium ionic radius for the sodium plus ion is larger than ionic radius for magnesium 2 plus. Magnesium 2 plus ionic radius is larger than the ionic radius of aluminium 3 plus. So across the period, the ionic radius will get smaller because the effective nuclear charge is increased. Betul ke tak effective nuclear charge will increase, so you can calculate by yourself the value of the effective nuclear charge. For trend of anion, going down the group, the principal quantum number n is increased, the energy level is increased, so then the anion will get larger. Okay, the same trend as the cation. As we going down the group, cation and anion will experience the same trend. As we going down the group, it will increase the energy level. So then the orbital will get larger. Cation and anion both will increase. The ionic radius for cation and anion will be increased. However, across a period, the isoelectronic anion will get smaller. Size of the isoelectronic anion will get smaller because of the nuclear charge increase. So the trend across period for both cation and anion is similar. When we cross the period, all the isoelectronic cation and all the isoelectronic anion will become smaller because of increase in the effective nuclear charge. Okay, next we go to ionization energy, trend in ionization energy. So first we have to know what is the ionization energy. Ionization energy, the definition is the minimum energy required to remove 1 mole of electron from the ground state in the gaseous state. So minimum ionization energy adalah energy minimum yang diperlukan untuk remove 1 mole electron, 1 mole of electron from the ground state. Ground state here meaning from the original state dia of 1 mole atom in the gaseous state. The greater the ionization energy, the higher the atom tendency to retain electron. Semakin tinggi nilai ionization energy, maknanya semakin susah untuk elektron tu di-remove. Semakin susah untuk elektron itu di-release. So factor that increase the value of factor that will affect the ionization energy is effective nuclear charge, shielding effect, and also because of the atomic radius. In ionization energy, we have the removal of electron will be removed in step by step, meaning that when we want to remove 3 electron from one element, so these 3 electron will not remove simultaneously, but then it will remove by step. So first it will undergo the first ionization energy to remove the first electron. It will undergo first ionization energy to remove the first electron, and then it will go the second ionization energy to remove the second electron, and then it will undergo a third ionization energy to remove the third electron. So the definition of first ionization energy and the definition of the second ionization energy you should know. So what is the first ionization energy? First ionization energy is the minimum energy required to remove the first electron from the gaseous atom in its ground state. So these are the two important terms here. Remove of 1 electron, minimum energy needed to remove first electron from the gaseous atom in its ground state. So the equation should be like this. Magnesium atom, when it achieves minimum energy to remove first electron, so then it will become magnesium plus ion. Plus 1 electron here, meaning it removes 1 electron. Magnesium in gaseous state, not solid, not liquid, but magnesium atom in its gaseous state, error, meaning that it will remove 1 electron, and then it will undergo it, and then it will form magnesium ion. It will form metal ion also in gaseous state. Second ionization energy is the energy required to remove the second electron from the gases positive ion in its ground state. Here, from the gaseous positive ion, after we remove the first electron, it will become gaseous positive ion. It will become M plus ion. So M plus ion in its gaseous state will release 1 electron to form metal, to form M2 plus ion. So the equation, how to write the equation for the first ionization energy and how to write the equation for the second ionization energy, you should know. So the first ionization energy is much um, is much is lower. The first ionization energy is lower than the second ionization energy. Second ionization energy is lower than third ionization energy, meaning that to remove the first electron is much simple, is much easy, then it required less energy than uh, than the step to remove the second electron. So to remove the first electron, it much simple, more easy than removing the second electron, than removing the third electron. So the trend of ionization energy in period table across the period, ionization energy will increase. Why it will increase? Because the atomic radius is decreased. Because the atomic radius is decreased across period, atomic radius is decreased, so the ionization energy will increase. Ionization energy will increase, meaning that it's more difficult to remove the electron because the outer electron are more tightly hold to the nucleus. So then we need more energy, we need higher energy to remove the first electron. Across the period, I repeat, across the period, across the period, atomic radius is decreased. So when the atomic radius is decreased, the attraction of electron towards the nucleus is increased, is higher. So the electron is more tightly held to the nucleus. So when the electron is more tightly held to the nucleus, so we need more energy. We need higher energy to remove the first electron. So that's why across the period, the ionization energy is increased. Going down the group, atomic radius is increased. Why atomic radius is increased? Because the energy level is increased. The principal quantum number n is increased. So atomic radius is increased. Average distance between valence electron and nucleus is increased. So the attraction of nucleus to the attraction of valence electron to the nucleus is decreased. The valence electron is loosely tied, is loosely held to the nucleus, and then the ionization energy decrease. Then meaning that we need lower energy to remove the first electron. However, that is the general of trend in ionization energy in period table across the period and going down the group. However, there are few anomalies in the trend. The first anomaly is okay, beryllium and boron. Beryllium and boron both are in the same period, both are in the period 2. So the general trend is across the period, atomic radius is decreased. So electron is tightly held to the nucleus. The attraction of nucleon is more higher to the nucleus, and the ionization energy is higher. We need more energy to remove the first electron. So this is the general trend across the period. However, there are anomalies, and the the anomaly happens in the boron atom, boron and beryllium atom. So in periodic table, beryllium comes first and then followed by boron, meaning that the uh, ionization energy of boron is more higher than ionization energy of beryllium. But that is not what happened. Instead of supposedly the ionization energy of beryllium is sorry supposedly the ionization energy of boron is higher than the ionization energy of beryllium, because beryllium comes after the boron. However, however, um however, the ionization energy of beryllium, supposedly ionization energy of boron is higher than beryllium. However, the ionization of boron is lower than the ionization of beryllium. Why? Because when we see the orbital diagram for beryllium, there are two electrons. There are there are pairing of electron in 2s orbital. The valence electron in beryllium is held in pairing, is in pairing, whereby the valence electron in boron is in single in 2p orbital. So this electron is to remove this electron is much easy than this to remove this electron is much easy than removing this electron. To remove the first electron from boron is much easier than removing the first electron from beryllium. So that's why the ionization of energy of boron is lower than ionization energy of beryllium. So it different from the general trend of the ionization energy across the period. So the same similar phenomena also happen in aluminium and magnesium. So to distinguish why, so to you have to you have to write the orbital diagram for aluminium and then write the orbital diagram for magnesium and see that the in valence electron in magnesium is more stable than valence electron in aluminium. So that's why the ionization energy trend of aluminium and magnesium is different from the general trend across the period. So also happens in nitrogen and oxygen in going down the group. The general trend when we going down the group, the atomic radius is increased. When the atomic radius increase, ionization energy will be decreased. However, there are anomalies happens in nitrogen and oxygen. Nitrogen and oxygen Nitrogen and oxygen have different trends. So both nitrogen and oxygen are in the same period, not in the same group. So why nitrogen and oxygen do not follow the general trend? Because of when you see in the nitrogen, all the electrons in the valence orbital are in single pairing. Why?